So, pretty short and sweet. If you have a question about this, if you just mark it and after class, or if we have time at the end of this one, I'll be happy to cover this. So it's the analysis of light from distant sources. Number one, what's known about the universe. That usually comes up in a test. I'll just tell you, that kind of question is what it is. And the next one as well, or something like it. Visible light constitutes just a little bit of the electromagnetic radiation spectrum. So you've got the spectrum that goes from radio waves to gamma rays, and it's a big spectrum. It covers all from nanometers to miles, and there's just a little teeny part of it that is visible for you and I to see. And the reason why we can't see, some of the wavelengths are too long for us to see, and some are too short. So, two ways light can be described by waves and discrete particles. Wavelength is the distance of one crest to another. Most waves are either too long or too short for us to be detected. Shorter wavelengths bend more than longer when they through a prism. So the longer ones, like the red, bend less. The shorter ones, like violet, bend more. Particles are called photons. Shorter wavelengths mean they're more energetic. The photons are more energetic, more lively. And so this one, number 9, worth 4 points. 2 points if you called the color right, red and violet, and 2 points if you got, or 1 point for each if you got what it exactly was. So 640 to 750 nanometers. That's the length, that's the wavelength of that wavelength. And violet is the shortest. Now, the radio telescope, the James Webb telescope, I showed that last time, but that telescope covers the infrared range. So it covers a range that you and I can't see, but it can pick out a very small wavelength, and it can look at that wavelength. And then it can pick out another small wavelength, and it has an acute. I can't remember right off how many nanometers, but it's a long span in the infrared wavelength, outside of our visible. So that was the only real question about. I gave points for the color, and I gave a point for the color and a point to describe what that color is. And that's, some of you like spectroscopy, the study of those particles, properties of light that are wavelength dependent. So that's looking at wavelengths. And these, if you just put these down, like the 3 kind of spectra, what are they? Continuous, dark line, bright line. If you put what they were, you got an extra point for each one you put down. So some of you got +3 on this thing. You got the regular score, but you added to it. And if you added to it and it was really adding information, if it was a continuation of a paragraph you were quoting that didn't add a lot of information, well then that was one thing. But if it added information to it, then I'll give you extra credit for it. Because that's how a lot of you in the number 4, Media Review 4, and so did the other class, the async class. So I've got 10 people in that class. So they were more zeroed in, but they're probably only taking 1 class anyway. So it's easier when you've got all these classes and all that's going on. You got a lot going on. But you're taking 1 class. Well, some people in this class and the other one mixed up what I was asking, and some of you like to be brief. You just put the most minimal, just a word down. Well, that usually doesn't accommodate what I want. I don't just want fluff, but I want just some description. If you describe what went on in that earthquake If you said that mudslides caused it, you were wrong. They talked a lot about mudslides, but it didn't have anything to do with the earthquake that they were looking at. It may have had to do with a tsunami at one time in history, but it couldn't have been recent because they had that flower growing out of there. So that said, the flower they estimated to be 10 years old. I'm not into sea flowers, so I don't know how they figured that, but I assume they did correctly. But I'd want more information about that. I just want it fleshed out. So if you choose to do those additional problems, 1 and 2, if you need to, you know what you got on both of them. If you got more than 75% on those, then I wouldn't bother with it. But otherwise, it might do you good. Won't hurt you. You're not going to be disadvantaged. So, how does a continuous spectrum reveal information about the surface temperature of a radiating body? So, on page 698, it says continuous spectrum, and then it goes along and it says a bunch of stuff. And it says some stuff that I wouldn't expect anybody to remember or even actually understand very well. It was in italics, and it says, the rate of increase is stated in the Stefan-Boltzmann law, which says, the energy radiated by a body is directly proportional to the fourth power of its absolute temperature. My friends, for most non-science people, that means nothing. It means almost nothing to me. When I read that, I'm thinking, okay, like, give me a number like 3,029,000,000. What does that mean? Big. Big. That's all it means. It doesn't have any value. I don't get anything from it, except it's big. Now, if I have to figure out something about it, I know how to do that. I know how to reduce it so it's manageable. I can use an exponent, and I can shrink it down so I can work with it. But just telling me what it is doesn't mean anything. So, quoting that quote, and there was one in there, I didn't go into it with volcanism. In fact, I avoided it this time, but there was one thing that a lot of people quoted 2 years ago about volcanism that I'm sure they had no idea what it was. I'm absolutely sure. But it was a quote, and it was under a heading, so. Well, if you read a little bit longer in this continuous spectrum, you read something that's understandable. It says, a continuous spectrum contains information about the surface temperature of the radiating body. Oh, what? Man. It says it. It actually says it. But you stopped with that italics quote and didn't go any further. But if you went a little farther, you'd see this exact quote here, and then it says, the surface temperature as the surface temperature of an object increases, a larger proportion of an energy is radiated at shorter wavelengths. Now I can understand that. I don't have to be a mathematician. I don't have to be a scientist. I can understand that. It increases, wavelengths get shorter. The hotter it is, the shorter the wavelengths you got. So that makes sense. So when putting down these answers, if you didn't understand it, if you quoted this, and now some of you may, but I would have just, if I started reading, I'd start a couple of words into that italics thing, and then I would have skipped down to the next sentence. I mean, I've been a student, as a professor, I would do that, because I'm not interested in that stuff. I want to get to this question that is being asked, so I'm going to key in to what that thing is, and that's what it says. How does this spectrum reveal information about the surface temperature of the radiating body? Well, I'm going to read, and I should come up something about this, and when I hit it, then I got it. Okay? So that's just it. Yeah, so that's it. So, what does an absorption spectrum reveal about a radiating body? Dark line or absorption spectrum reveals the composition of the radiating body. And each chemical element, I don't know that it's interesting to you, but it's interesting to me that each chemical element has its own individual line spectrum. It's like a fingerprint. Two aren't the same. So each one, you can find out. If it's hydrogen, you can find it'll show up as hydrogen. If you look at a spectrometer, you can tell what chemicals are in that thing. And they're individual, okay? And the Doppler effect, I think most everybody got this. If it's going away, the wavelengths are lengthened, which would tend to produce a redder appearance. If they're coming toward you, they tend to be bluer because they would decrease. Increase, they're lengthened, they produce redder. They're shortened, they have a show of blue shade. So that's it. I thought. So I'll probably eliminate this from the video for the async because I don't know if they have all turned it in yet. So that is that. And I think we covered everything that I had to cover. Yeah. And so I passed out to you, and you who weren't here then, the two of you, I passed out the wavelength 1 and 2 that has the answers on there. We just didn't have time. I had it last year, we didn't have time, and if I go over the test at all, we just don't have time to cover all that stuff. So this is starting with the handout that I gave you right when you came into class, and you looked at that paperclip thing, stacked full of things that we had to go through, and you looked and say 3 pages, there are 6 pages in here of all this stuff, and so I'm sorry. Kinda, well, I am, I mean, I was a student, I helped, so I had to go through this, some of you heard this before, if you've heard me math, but, so when I went to graduate school, I didn't plan to go to graduate school, I didn't take the math that you were supposed to have to go to graduate school, you had to have a certain level of math, and I didn't have that, and, but God wanted me to go, so I went. Well, my math class, during my graduate level math class, I would sit where you're sitting, and the teacher would be talking, and I read the math book. I even went to the library and checked out math books, trying to figure out what in the world he was saying. After 15 minutes of intense concentration, my mind just went. I had no idea, after the first 15 minutes, what he was saying. Every class period was like that. And I tried. In my first test, there were 4 tests in that class. Or there was a paper and 3 tests. So you have, each one was worth 25% of your grade. My first test in that class, I got a 47. The class average was 87. That included my 47. So it took me a couple days to get over that. I mean, I didn't just do like we heard in chapel today, say, oh, praise the Lord for a 47. I didn't. I thought, God, you put me here. I didn't want to do this. I tried. I've got books out of the library on math, for goodness sakes. Well, so after a day or two, I calmed down. And then the only other Christian in that department, in agricultural economics, only other Christian, a guy from the Philippines, Benny Arago, came into my little cubicle on the 4th floor and said, I'm quitting. I'm leaving school. I said, why? She said, well, I just failed that math test. I said, well, don't quit. Don't quit. If God has you here, He'll help you through it. Now, I came. It took me a couple of days to get there, day or two, but I did get there. She says, yeah, well, what did you get? Well, I showed him, got a 47. He got a 67. He failed it. But I failed less than him. It was the best grade I got in graduate school. Because he didn't quit. He didn't quit. You think, well, I failed. Well, I did. But my failure encouraged him to stay. And it was worth it. It was worth it. It was the best grade I got. Ended up getting a B in the class. So, it's okay. I mean, you don't want to get less than a B in graduate school. That's kind of failing. But I did okay. But I'll never forget, well, I can't say that. Up to this point in my life, I've never forgotten that experience of failing so somebody else would continue to press on. And we don't like that as Christians. We think, well, God, I presented my body to you. Shouldn't you take me to a dentist that does good work? Man, I wish he did. I've had terrible dental work. I grew up having great dental work. I've had terrible dental work that it cost me thousands of dollars to repair. But every time I've gone to the dentist, God has opened up a door to share Christ with somebody in the waiting room, pray with a nurse or a hygienist. I mean, one thing, it's been great. I can't complain. So if he wants to use my body in a way that's inconvenient for me, I want him to be able to do that. I don't want to just go around and go to the worst dentist around. I don't want to do that. But I want to be willing for him to use me how he sees. And a lot of times that won't line up with me. But that grade, I'll tell you, that grade was the best grade. And I don't begrudge. God has provided the money to fix my teeth. So I've still got them. Most of them are mine. Hallelujah. So, here we go. Back to unreality. What I just shared with you was reality. This is not. But it's not exactly fiction, or non-fiction, or fiction, yeah. Yeah, that's right, either one. So electromagnetic spectrum, you have that on this, we should be tracking. If I'm not tracking, if you're not tracking with this, with the paper you've got, then tell me, because. Okay, stars. In addition to visible light, emit, emit X-rays, radio rays, all kinds of stuff. So, and here we have radio at this side. Sometimes they have this reversed, and radio's over here and gamma's over here. It's not a matter of which direction you're going, but the idea that you follow through. So you've got wavelengths that are longer, and they get shorter and shorter and shorter. Right here is visible. And then we got ultraviolet, X-ray, and gamma ray. So, so the wavelength scale, 10 to 30, okay. Frequencies, so the frequencies get shorter frequency here. And temperature is increased here as well. So all forms of electromagnetic energy travel through space at a speed of 186,000 miles a second. That's a rough, that's not the 186,228 or something like that, but 186,000 miles a second. They travel through space, which is a vacuum. If it travels through other things, it may not travel that fast. Frequency is the number of waves that pass by a point in 1 second. Wavelength, so frequency, that's from crest to crest or trough to trough. That's how many waves pass by that point in 1 second. Wavelength typically is the distance from one crest to crest, but can be measured from any point to the identical point on the next wave. And amplitude, the vertical distance between the tip of the crest and the wave's central axis. So that's when you have the wave so you got a central axis here. So the amplitude is like this. Central axis, these are would, if this was drawn to scale, it'd be, they'd all be equal and look real nice. So, picture. So that's what it is, amplitude, crest, trough. So you could measure the distance from crest to crest, from this point to this point, from this point to this point, from trough to trough. But you're just measuring that one wavelength then. from the beginning to there, or you can move it from crest to crest, trough to trough, but you're covering one segment there. Frequency and wavelength are inversely proportional. This should be good to remember. The lower the frequency, the longer the wavelength. So red would be lower than violet. Violet would be shorter than red is longer. The longest is red, of the visible spectrum. The longest wavelength is red, the shortest is violet. And then there's a bunch in between. High frequency equals short wavelength. Gamma rays have a high frequency and short wavelengths. Radio waves, longest. So this here, how many of you have been here, been to this place? Anybody travel with singing group or drum team? Did you ever get up to Green Bank?
No.
It's I forget what the name of the camp is. It's a camp, and you can walk across a field with this thing. That's right. You can just walk across the lawn, climb over a fence and walk across the field, other side of the fence, and you can be there. I've been there a number of times with a singing group in the past. This thing, this is the Green Bank Telescope in Green Bank, West Virginia. It's the world's largest fully steerable radio telescope. So they can steer this thing around. It's on tracks, they can steer it around.
Oh, yeah, I've been there.
Have you? Yeah,
That's, right down the road from where Diana lives, actually.
that's right. Yeah, where folks live.
Yeah.
And her grandpa, there used to be a train, and he used to be the engineer of the train.
Yeah.
I've been in that train with him, engineering. Anyway, so this telescope weighs 8,400 tons. And it's 485 feet tall. It's big. And the surface area is 328 by 361 foot active surface. And it's got 2,209 laser actuators. It's got little plates. And all these little plates are controlled by little laser motors, or laser controlled motors. So all these 2,000 some plates in this thing can all be moved to focus on different things. So they got 2,209 laser actuators, small motors used to adjust the position for the 2004 surface panels. So there are 2004 surface panels, and they got these motors and they're laser adjusted. They're really tight. So this thing and these mirrors, the aluminum is manufactured to a surface accuracy of better than 2/1000ths of an inch. So these mirrors, these aluminum plates, the tolerance is better than 2/1000ths of an inch. So and you have 2,004 of them, and they're all operated independently. They can operate these things to pick up radio signals, trying to find life somewhere else. So it's a pretty neat thing. If you've ever been there, I mean, I've been twice, and if I was in the area, I'd go again. It was very interesting. So, anyway, that's there's a lot of stuff. And I think you could probably do it. I don't do it for this class anymore, but, you know, they have a NOAA weather station up on the hill, out of town a ways, and then a NOAA weather station. And it's really interesting, and they are glad to have people come and visit. If you want to go, the manager, he goes to the Methodist church in town, Sean Harley. He used to manage there, but we used to send groups out there to do a kind of earth or science thing, and they talk to us about it. They show us around the rooms and all the models that they have, trying to figure out what weather is going to be in eastern Kentucky. It's a lost cause. But anyway, they try. So most ultraviolet light, X-rays, gamma rays, and infrared wavelengths are absorbed or partially blocked by the Earth's atmosphere. So most of these wavelengths, that can, a lot of them, especially X-rays, gamma rays, but other can do damage to our bodies, or human bodies, are absorbed or blocked, partially blocked by the Earth's atmosphere. God created things, he knew what he was doing. And so to collect data on the source of these wavelengths, instruments are needed to go beyond the Earth's atmosphere. You got to go beyond that to find out what's going on with these things, what's being radiated. The Infrared Astronomy Satellite, this is an old one, launched in '83, was the first space-based observatory to perform a survey of the entire sky at infrared wavelengths. So it was calibrated to look at the sky at an infrared wavelength. They had narrowed down what wavelength to study. And so they took a wavelength, or a particular wavelength, and studied the whole sky at that wavelength. And then they could switch to another wavelength, infrared in this case, and study that. So they tried to compile what space was looking like, looking at the wavelengths. And so it operated 10 months. It detected over 250,000 sources of infrared energy. So the micrometer wavelengths, it was 12, 25, 60, and 100. I don't know why they chose that, but they chose those to look at that. And then 350,000 total sources, including 10,000 previously unknown galaxies. So this was in '83, they launched this thing. So that's an old one, but that's what it was doing. It was looking at the sky, and it was looking at particular wavelengths. It was zeroed in to calibrate. It wouldn't see if it was looking for 25 micrometer wavelengths, it wouldn't see the ones at 26 and 24, and either way, it would just focus on that. So, the Hubble launched in 1990, orbits the Earth every 97 minutes at 353 miles above the surface, traveling about 5 miles a second, so it's out there now, it's going around. It has instruments that collect data as well, and astronomers around the world compete for time use. That's the same way with that Green Bank telescope. It's used for astronomy about 6,500 hours every year, with between 2,000 and 3,000 hours per year going to high frequency science. So they're looking at frequencies, they're doing it wavelengths. That's what they're keying that Green Bank telescope in on. Well, they've gone 353 miles above our Earth to look at what's going on out there in space, and that's what they said, the Hubble up there. And primarily the instruments examine ultraviolet, near ultraviolet, visible, near infrared, and infrared wavelengths. So visible and a little bit on each side of visible. They're not looking at radio waves, but they're looking. And the Voyager, well, you don't have that. The Voyager was powered by the sun, and they're still out there. I haven't looked recently where the Voyagers are, but they've broken through our solar system, and they're out there. So this is Hubble. That's the Hubble telescope going around at 353 miles above our Earth and taking pictures. These are colored. These are colored. They didn't just take this picture and it was like this, like I take my camera out and take a picture. They have wavelengths, and they colorize the wavelengths so you can see the distinctions. That's what they did with James Webb. So Hubble's successor, the James Webb Telescope, is orbiting about 1 million miles away from Earth. So it's way out there. And the James Webb Telescope, I don't know, sir, if I have this. Yeah, you don't have any of this. You don't have this. You have what it was just above. You said 1 million miles, about 1 million miles, 940,000 something, but 1 million miles. So it's a lot bigger than Hubble, a lot bigger. And it is. So this is our Earth, and this is our sun. And this telescope is operating out here on the other side. And this platform is a shield, because this telescope has to operate at something like 300 plus degrees below 0 Fahrenheit. It's got to be really, really cold to be effective. So radiant energy from our sun, even from the Earth and our moon, can affect it. So that's why they have this big shield in the back. This shield shields this huge thing, and these were in pieces. And the one thing about this one is, with the Hubble, in fact, they had some problems with it, and they sent people in spacesuits out to correct it, out to fix it. And then they set it back operating. Well, this is 1 million miles away, they can't do that. So if this breaks down, it breaks down. So far it hasn't broken down. It's taken some incredible pictures. So this shields it. Where it's operating at that right here, it can operate here, and this is the one place as it maintains this orbit. Then it's able to shield itself. It's not getting to a place where the Earth is behind it and going to reflect light into it, or the sun. It's going to maintain a position where it is always protected. And this L2, I'm not going to get into that. I've read about it enough to understand that there are 5 points. Some mathematician, they figured there were 5 points where something could orbit and be in conjunction with the Earth, and that L2 is one that they set up this, and apparently is working. So, okay, this is the difference between the Hubble. So the Hubble's telescope was looking at a little bit of ultraviolet, visible, and a little bit here of infrared. So that's what it was seeing. The James Webb is taking this infrared range. Now there still is more infrared that it could take, but it's taking this range of infrared and just examining that in space. That's all it's doing. It's not looking at visible light. It's not looking at ultraviolet, X-ray, or gamma rays. They're all out there, but it's not looking at them. It's looking just in the infrared range. So, I'm going to do this. Okay. So I'm going to cut in. Okay. I just about got it there. Okay, so I'm going to start here in this thing, in this lecture. But he goes into detail about the James Webb Telescope. And then he goes and talks about what they're seeing with this telescope, okay?
engineering marvel. It really is. You can't just put it anywhere. You can't put it close to the Earth. Hubble's in Earth orbit. Can't put James Webb in Earth orbit. Why? Because the Earth gives off heat. It would heat up the spacecraft too much. So what they did was they put it at what's called the L2 Lagrange point. There was a mathematician, Lagrange, who figured out that there are 5 locations relative to the Earth and Sun where you could place an object to give it just the right speed. It will orbit at the same revolutional speed as the Earth. So it'll maintain its position relative to the Sun and the Earth. There are 5 of these locations. They're indicated by L1, 2, 3, 4, and 5. And the James Webb Space Telescope is at L2, which is beyond the Earth. It's about 1 million miles into space, beyond the Earth, the opposite direction of the Sun. And so not only does the Sun shield protect from the Sun's heat, but also the little bit of heat that the Earth gives off as well. So that means it's not accessible, it's not repairable. When they launched it, if something had gone wrong, that would be $11 billion down the drain. Fortunately, it worked. So we were all real happy about that. An amazing spacecraft, and it can see deeper into space because it's designed to look in these frequencies that galaxies have when they're very far away. Far galaxies are redshifted because they're moving away from us very quickly, so their light's been shifted from the range that Hubble can detect, that you can see. They'd be invisible to us, but the James Webb Space Telescope can see them because it sees these lower frequencies of light, these infrared frequencies. Now, secularists made a number of predictions about what they were expecting the James Webb Space Telescope to find based on their belief in the Big Bang in the billions of years. And here's what they were expecting. They were expecting fewer galaxies at great distances and none beyond a redshift of 14. Why? Well, remember, in the secular view, as you look out farther into space, we know the redshifts get deeper, but in their view, as you look farther into space, it's kind of like looking back in time because you're seeing the galaxies when the light was emitted, which they believe was billions of years ago. So if you look out beyond a redshift of 14, that corresponds, in their view, to a distance and a time where galaxies haven't formed yet. So they believe you're looking back in time, and you should see a time when there aren't any galaxies. And of course, before you get to that, you should see relatively few galaxies, right? Because you're looking back to a time when there were only a handful of galaxies in the universe, because it takes time for those galaxies to form as the stars form and collect into the galaxies. And so you'd expect to see very few at a redshift of 14, and really none beyond that. And the farthest galaxies you do see ought to be babies. Low mass, clumpy galaxies that have just formed. So, the idea is that when galaxies first, they start with a few stars, and then more stars get added, and then they collide with other galaxies and gather more stars. They get more and more massive, and they become more well-structured over time. So these beautiful spiral galaxies, those are thought to be relatively recent. The early universe shouldn't have those. The very earliest universe should have no galaxies, and then as you get a little closer, you have a few, but they're baby galaxies. Low mass, clumpy, and irregular. Finally, they expected that these farthest galaxies would have no what are called heavy elements, or metals. Now, in astronomy, the heavy element's anything beyond the first 3. So if you look at the periodic table, you got hydrogen, helium, lithium, everything else is a heavy element in astronomy. And the reason for that is the Big Bang is supposed to produce the first 3 elements, hydrogen, helium, and lithium. The Big Bang is supposed to start with pure energy, and as it cools, those elements form, but the conditions aren't right to form any other elements. The temperature and density are such that you can only get hydrogen, helium, and just trace amounts of lithium. None of the heavy elements are supposed to be made by the Big Bang. But we do have heavier elements in the universe. We've got oxygen and carbon, stuff that we're made of. So how do the secularists account for heavy elements? Well, they would say that stars make the heavier elements in their core. But only the largest stars will do that. The very largest stars, they have such a high temperature and pressure in their core that eventually they're able to fuse and synthesize the heavier elements, oxygen, carbon, and eventually things like iron and so on. And then when these stars explode, which does occasionally happen, they spread those elements out into space, and so that the next generation of stars has a little bit of these heavier elements in it. That's the idea. So the idea is the first generation of stars should have only the lightest elements, right? If the Big Bang can only make hydrogen, helium, and lithium, if the only thing in the universe is hydrogen, helium, and lithium, when the first stars form, what would they be made of? Hydrogen, helium, lithium. That's it. There isn't anything else. So the first stars, which would be called, if they existed, they'd be called population 3 stars, should have no heavy elements at all. No oxygen, no carbon. And then the next generation of stars, when some of those stars explode, they make the heavier elements in their core, and then they explode, and the next generation of stars has more heavy elements, and then the third generation has even more. So those would be population 2, population 1. It goes backwards because of discovery reasons. Anyway, farthest galaxies should have no heavy elements because they haven't had time to form yet. Those are the secular predictions. You got it? Look far enough, you'll see a time when there were no galaxies. You look close to that, you'll see very few, and they ought to be baby galaxies, clumpy and irregular. And the galaxies that you do see, those far ones, should have no heavy elements. But that's all based on the Big Bang. I don't believe the Big Bang. I believe in biblical creation. And so I thought, you know what, I'm going to make some predictions too. And so back in January of 2020, I wrote down my predictions. I published them. My predictions are basically the opposite of these. And I'll tell you why that is. I predicted that we'd see lots of galaxies, even at great distances, even beyond redshift of 14. Why? Because I don't believe we're looking back in time. I believe we're seeing the universe as it is, according to the definition the Bible uses of now. And so I don't think God stopped creating galaxies at a redshift of 14. I don't think we're looking back in time toward a Big Bang. I think we're just seeing galaxies at greater and greater distances, and I don't see any reason why God would stop at a redshift of 14. I think He'd continue to make them, probably forever. So I believe in lots of galaxies, even at great distances beyond redshift of 14. I don't think they'll taper out. I think they'll keep going. And the galaxies that we do see, the farthest ones that we see in the James Webb Space Telescope, they won't be baby galaxies. I don't believe in baby galaxies. God made Adam and Eve as adults. I believe He made the galaxies as adults. When God made the stars also on day 4 of the creation week, He made them pretty much like they are today. Some of them have exploded since then, but the farthest galaxies will be fully formed, which means they'll be massive and well-structured, like nearby galaxies. Not baby galaxies, not clumpy and irregular. Okay? And I believe the farthest galaxies will have heavy elements. Why? Well, I have an advantage. I have the history recorded in the Bible, and I believe it. That gives me an advantage. I know from Scripture that not all heavy elements were formed in stars. And by the way, I do think it's possible for the largest stars to produce heavy elements in the core. I think there's some good science there. But see, secularists believe all heavy elements were made that way, including the heavy elements that make up the Earth. You might have heard secularists, Carl Sagan or Neil deGrasse Tyson, say, we're all made of star stuff. That's what they mean. They mean the elements like oxygen and carbon that make up our bodies were forged in the core of a star. But I know better, because I know the Earth was made before the stars were. Earth's made on day 1. According to Scripture, stars are made on day 4. Is Earth made of star stuff? No. Earth was here before the stars. And I know Earth had oxygen in it before the stars. Why? Genesis 1, God created heaven and the earth was without form and void, and darkness was upon the face of the deep, and the Spirit of God was hovering over the waters. So the earth had water on it on day 1. Water is H2O, O is oxygen. So oxygen existed on day 1 when the earth was made. Stars aren't made until day 4. So the oxygen on the earth did not come from stars. It preceded the stars. So I believe that the farthest galaxies will have heavy elements just like the nearby galaxies, because they're made as adults, just like Adam was. Now, I gotta tell you guys, I believe the Bible, and I have enough confidence in it that I was willing to not only put these claims out there, that these are the opposite, these are the exact opposite of what the secularists are saying. I was so confident that they would be wrong that I even predicted, I tried to predict how they would respond when they found out they were wrong. Because what they're going to find is they're going to find galaxies far beyond redshift of 14, where there shouldn't be any, because they haven't had time to form yet. I predict that instead of giving up the Big Bang, because that's their sacred cow, they're not going to give that up. What they'll do instead is just push galaxy formation back to an earlier time. They'll say, well, I guess galaxies formed a lot earlier than we thought. So here's my prediction. Secularists will respond to their failed predictions with statements like, Webb discovers that galaxies formed much earlier than previously thought. That's my prediction. So, and you can find these predictions on the website, Biblical Science Institute. The article is the James Webb Space Telescope. This was published January 21st, 2022. This is before James Webb had taken any data. It didn't release data until July that year. Okay, so this is months before we had any results. So what did they find? Well, they pointed the Webb telescope out to a section of our galaxy relatively empty, Did they find that galaxies stop at a certain distance? Here's what they found: galaxies upon galaxies upon galaxies. How about that? And they're in incredible redshifts. Some of them well beyond a redshift of 14. Redshift 16, 18, one of them we think has a redshift of 20. That is way beyond what the secularists were expecting. By their math, that puts it at a time of like 300 billion years after the Big Bang. Galaxies should not have had time to form yet. But there they are, and there's lots of them. How about that? Isn't that beautiful? What you're seeing there, even those tiny little dots you're seeing in the background, those are not individual stars. Those are galaxies with hundreds of billions of stars each. The tiniest little specks you're seeing there, those are galaxies. The distances are outrageous. What are the results of the James Webb Space Telescope data? First of all, lots of galaxies at great distances, even beyond a redshift of 14. Again, some of them out to a redshift of 20. And a lot of those are being debated, but some of them have been confirmed already, so that's pretty neat. What about these farthest galaxies? Are they little baby irregular galaxies? No. Farthest galaxies are fully formed, massive, and well structured. You can see that in those images. You can see that there are spiral galaxies out there. They're big. They're massive and well structured. Spiral galaxies. They're not clumpy, irregular baby galaxies. Even secularists have admitted these galaxies are as massive as galaxies nearby. They were not expecting that. They were not expecting that. What about heavy elements? Are they devoid of heavy elements like the secularists expected? No. The farthest galaxies have detectable heavy elements. The James Webb spacecraft has a spectrometer on board which can break the light into a spectrum and identify the atomic elements that made the light. And it's detected heavy elements like carbon and oxygen in these distant galaxies, not the population 3 stars that are devoid of such elements. Pretty neat. So in all cases, the creationist predictions were right. The secular predictions are what we call wrong. They're just dead wrong. What about my prediction about how they would respond? I predicted they would say things like, here's my quote of what I'm expecting them to say: Webb discovers that galaxies formed much earlier than previously thought. How did they respond? Here's a quote: galaxies started forming much earlier than many astronomers previously thought. That's from UConn Today, August 9, 2022. You can look it up. Here's another one: massive galaxies formed earlier in the universe than previously known. Nature News, July 27, 2022. Here's another one: evidence is building that the first galaxies formed earlier than expected. Earlier than you expected. Not earlier than we expected. That's the Sky Telescope, January 10, 2023. Here's another one: a lot of galaxies could have been formed in the universe much earlier than previously thought. Space.com, January 12, 2023. I can go on and on. I found dozens of these headlines. I was trying to find...
Now, I will, the sheet that I have here that I will put up for you has this. If you want to watch this, I started around 29 minutes of this. And I looked up his article. I found it. It didn't, he might have said other things. I didn't find everything that he said in that article. There were a couple of things that he clearly stated that are clearly, and I believe he did. If he wrote out what they were going to say, out of confidence he did what was right. I didn't find everything like he listed, like bang, 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 but there were clearly a number of things that he did say in that article in 2022. And it was before the Webb didn't get in place until July of 2022. It didn't get in position to start taking pictures. So when he wrote his article, it was before any information would have come back from that telescope. So it was interesting. I just like to, I like to check out, since I'm so smart, I just like to check out to see if, because Christians they can overemphasize something, they can put a spin that is just, and if you're dealing with secular science, boy, you need to be honest. They need to be able to say, oh, okay, and if they can go to your article and they can find that you said 3 things that were okay, but the 4th one was bogus, then you don't want to do that. So, okay, so we will start with let me see, is that, okay, so we got through 1 page, oh man. Well, I just thought that was interesting to see him looking at what you're seeing or what you can see, and if you want to get on, you'll be able to get on that if you want to follow through. And I want to give you advice, so I'm not gonna say that there's gonna be any test questions, but I had a professor at Virginia Tech that he had D answers, C, if people wanted a DM a test, he thought level D questions. That you could get enough of those questions right and get a D. And then he had level C, and then he had level B, and then he had level A. And if you wanted to get an A, you probably had to know something about level A. You probably had to know something that you weren't being told to look at. So I don't know that any of this information, but it could appear. You could find something we just spent 12 minutes on a video. He didn't say anything that hasn't been said here. In fact, I said some of the things he said last time. So you've gotten it twice at least, plus it's in this thing. So, I don't expect you to memorize everything he said, but some of the things, in general, it wouldn't be bad to know. Okay, so